Hello, welcome back to my class series on engineering chemistry 21CHE1222 that is offered by Visvesvaraya Technology University. It is common for all first year students of VTU. Okay, in previous class I explained about the engineering materials in which the cement I explained. This particular class video it is covering that of polymers. And coming classes I'll be explaining conducting polymers and biodegradable polymers. So please be with me in my YouTube channel, my intuition. So this particular class video covers the topic like introduction to polymers, synthesis and applications of polyurethane, polymer composites, and about the Kevlar fiber. Okay, available in my YouTube channel, my intuition. Please do like my videos, share the videos to maximum. A polymer, it is any of a class of natural or synthetic substance composed of very large molecule called macromolecules, which are multiples of a simpler chemical units called monomers. We already know about this, about monomers and polymers. Mono, the word mono in Greek we call it as a single, and mer, mers, that is parts. So single parts, monomers combine to give a polymer. Poly in the sense that is a big, very large. Okay, therefore when monomers joined, even for a chemical substance to become monomer, that is a very important topic. It should have a bifunctionality in the same chemical. It should have two functional group which can react, so that a chain reaction is possible. The reaction takes place on either side of the molecule, or you can say two functional groups work together to become a long chain. Or it should have a double bond or triple bond. A double bond or triple bond, the pi bonds or weaker bonds, it can also be treated as a bifunctionality. Okay, so a monomer, a chemical with a bifunctionality, we call them as monomers. In the reactor, it gives a corresponding polymer, which is a big molecule or macromolecule. Now, polymer, it can be natural. Okay, we may not be need to synthesize in our lab. They are already available, natural synthesis, natural process like our protein, cellulose. So those are having. They are also polymers. If you check in detail about its molecular structure, we can see the repeating units of the monomers. So it can be natural, it can be semi-synthetic, or it may be completely synthetic. Semi-synthetic means natural polymers, we are modifying it, doing some alteration, chemical modification, it becomes semi-synthetic. The polymer, it may be in the form of plastic, rubber, resin, or fiber. Okay, so we'll take the examples, the types, the form, type, and examples. If you take in the form of plastic, plastic is a the type. It is a very hard material compared to resin or rubber. Okay, example cellulosic plastic, which is having cellulose origin, like celluloid or cellophane. Then vinylic plastics, which are having that vinylic functional group, like polyolefins, polyethylene, polypropylene, polytetrafluoroethylene, or polystyrene, polyvinyl chloride or PVC, polyvinyl acetate, polyvinyl pyrrolidine, etc. comes under vinylic plastic category. Then polyacryloids like polyacrylic acid, polymethyl methacrylate, that is PMMA, also called as plexiglass. It is used, it is having high transparency, therefore we call it as plexiglass, polymethyl methacrylate. Then next one, that is rubbery type. Rubbery type, they are having the rubber nature, elastic nature is there, but it is still a polymer. If it is a natural one, that is our natural rubber, which we collect from the rubber tree, so-called rubber tree, Lataparcha. Okay, so polyisoprene, cis 1,4 form of polyisoprene, that is the natural one. Trans 1,4, that is a synthetic one. Synthetic rubbers examples, if you take polydienes like polybutadiene, polychloroprene, they are synthetic rubber. Even butadiene copolymer, butyl rubber, silicone rubber. So butyl rubber and are very important because they are used in the tire manufacturing industry. Now resins. Resins are the soluble or the liquid form of polymer, I can say. It may be water soluble, like natural gums, which are extruded from the plants, or some of the natural gums which are obtained by the bacterial or the microbial action. Also, we get some polymers. We call it as natural gums like xanthan gum or agar gum. gum trachagand, gum acacia, many other. Then it modified starch, then cellulose derivatives, polyvinyl alcohol, polyacrylic acid, polyacrylamide. There are water soluble resins or water soluble polymers, which we call as the resins. Even some of them are water insoluble, but still having the resin nature or the semi-liquid nature. Resin in the sense liquid or semi-liquid. Epoxy resin, a well-known resin which is used for the composites preparation. Polyester resins, polyurethane resins, silicone resins are water insoluble because they don't have the functional group or which cannot form interaction with the water molecule. Therefore, they are water insoluble. Fibers, it may be natural fibers like cotton, wool, silk. They are naturally available fibers which are polymers, or semi-synthetic like viscose rayon, acetate rayon, promonium rayon. There are semi-synthetic fibers which are used in textile industry. Then polyamides, nylon, Kevlar, polyesters, acrylics, polyurethanes, etc. In which polyester is simply called as polyester, which is mainly used by textile industry. And nylon, it is used to make the ropes. Kevlar, it is mainly used as a fiber in composites, polymer composites. It gives maximum strength to that. Then polyurethanes, one of the example from that as per the syllabus, polyurethane. They are the class of extremely versatile polymer containing urethane linkage. Extremely versatile means these polymers are having a different, its own unique applications. Therefore, we call it as versatile polymer. Polyurethane, it can be used in the form of a foam, cushioning effect. It can be used as a resin. It can be used as a thread. Polyurethane threads can also be used. Okay, it has got a urethane linkage, that is NHCOO. So that urethane linkage I am drawing here, NHC double bond O, single bond O, single bond. Okay, so this functional group, if it is there, or this linkage, if it is there, we call it as urethane linkage. And the polymer which contains this particular linkage, we call it as polyurethane. Synthesis of polyurethane, or the requirement, monomers required for polyurethane. Polyurethane, actually it is a condensation polymer, or the reaction that happened to get the polyurethane, it is condensation reaction. Condensation reaction of that of a dialcohol as well as a diisocyanate. Okay, therefore dialcohol or diol, it's one of the monomer which is used. Ethylene glycol, for example, ethylene glycol, we know it's HOCH2, CH2OH. Even diethylene glycol also you can use HOCH2, CH2O, CH2, CH2OH. Or it may be 1,4-butane diol. Butane means it contains 4 carbon atom. 4 carbon atom. It also contains diol. Position 1 and position 4 having OH group. Therefore, it is 1,4-butane diol. That is HOCH2, CH2, 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 OH. Then 1,6-hexane diol. Okay, so we need a 6 carbon atom here, and OH on position 1 and position 6. Then some of the diisocyanate include. Diisocyanate means isocyanate group 2 times it is there, or more than 2 times if it is there, then also it is okay. Okay, this MDI, that is methylene bisphenyl isocyanate. It consists of 3 isocyanate groups. Okay, so the minimum requirement for a chemical to be treated as a monomer is bifunctionality. If bifunctionality is present, then that polymer will usually give a linear polymer. Okay, so what I drawn here, that is the structure of methylene. I'll draw it again. Okay, anyhow, you can pause the video and check it. So I start with the CH2 benzene ring connected to N double bond C double bond O, that is the isocyanate group. Okay, like that another benzene ring is present, which also has got that isocyanate group NC double bond O, CH2 CCH5, that is benzene ring, that is CCH4, N double bond C double bond O. So that is phenyl isocyanate, which it consists of 3 isocyanate group. It can give polymer reaction when takes place. All the 3 directions, so the right side, left side, as well as the 3-dimensional side. So 3-dimensional it can undergo the reaction. Therefore, it will give a network of polymer. So you'll get a cross-linked polymer or a a polymer network can be prepared. For usually say cross-linked polymer can be prepared. Another example, that is toluene diisocyanate. Toluene diisocyanate, toluene molecule that we know 6CH5CH3 is toluene. Toluene diisocyanate means it consists of two isocyanate group, one at ortho position, one at para position. First one I drawn, that is here you can see this is at ortho position, sorry, para position, and here I am drawing one more, that is at ortho position with the CH3 group. Hexamethylene diisocyanate, that is hexamethylene, 6 carbon atoms. Okay, so 6 carbon atom in a line I drawn, then NC double bond O. Okay, so that is isocyanate functional group, isocyanate functional group. Then again another isocyanate functional group is attached to it. Linear and network architecture of polyurethanes. Polyurethane based on the monomer used. If the monomers are having only bifunctionality like a diol as well as diisocyanate, it will be giving linear polyurethane. Whereas if any one of the monomer, either we use a polyol or we use a polyisocyanate, not a polycyanate, polyisocyanate, then also it will give network polyurethanes. Okay, we'll take the example of linear one here. Okay, I'm taking a diol is taken, then diisocyanate I'm drawing here. So this is a diisocyanate in which R represents the hydrocarbon group, hydrogen and carbon, or any other alkyl group. R dash also represents any alkyl group. Then another diol I am representing because I want to show the chain formation. And here also we know that oxygen, alcohol oxygen, it has got a lone pair of electron. This oxygen also got a lone pair of electron, and here with the presence of C double bond O, this double bond with oxygen is more electronegative than that of carbon, that you already studied. There will be an electron pull towards oxygen. That means this carbon is electron deficient comparatively. Therefore, this oxygen can give donate its lone pair. It can attract, or it can form a bond with this carbon. Okay, therefore this is the formation. Then that double bond with nitrogen, it breaks. Then nitrogen will get more electron density. It will attract one proton from that OH functional group. The same thing is possible on the other side. Either side of the polymer also, monomer also, the same thing it is possible. And finally we'll be getting the reaction. You can see that the oxygen is connected to the carbon having double bond with oxygen. Then it is connected to nitrogen. Then the nitrogen is attached to the hydrogen. Okay, so further R group, it is a RASH. Then nitrogen connected to carbon double bond O. That nitrogen got that hydrogen is attracted to that nitrogen. So NH bond is there. Then O, R dash, OH. Okay, so the same thing represented here. N number of diisocyanate and N plus 1 number of diol when it reacts, we'll be getting corresponding polyurethane, in which NHC double bond O, that is the urethane linkage, and we call it as polyurethane. So this is the general representation of the formation of synthesis of polyurethane. Now the additives which are used in the preparation of polyurethane for their applications and their different roles. So polyurethane, when we prepare, we need to add many additives to, so that the polyurethane will be having some application. We can use it for application. So those, anyhow, it consists of monomer, then other additives. So what is the reason for presence? Polyisocyanate. Polyisocyanate, it is responsible for the polyurethane's reactivity and the curing property. Curing property means how fast it will become solid when it is put into a mold to get the desired shape. How fast it gets the desired shape of the article, that is curing property. Then polyols, that is dialcohols, or many alcohol functional group. So polyols, they are the monomers. They contribute towards the flexibility of the long segments. So we have seen that the structure of polyurethane, which consists of that oxygen connected to carbon and carbons. So that oxygen, wherever oxygen present, there it is more flexible. The chain is flexible. Therefore, the polyol which contribute towards the flexibility of the long segments, and the polymer becomes soft, elastic. Then catalysts are used. Catalysts are usually used to speed up a chemical reaction. The same way here also we use different catalysts while preparing polyurethane. Plasticizers are added to reduce the hardness of the material. If plasticizers are not added, the polymer will become very hardened one. So to make it a little bit softer, different plasticizers are added. So there is a different topic only plasticizer, catalyst. I'm not going in detail. Okay, so pigments. The pigments are coloring agents. Different coloring agents are used to get to the aesthetic appearance for the article which we prepare using polyurethane. Then cross-linkers or chain extenders are used for the modification of the structure of the polyurethane chain, which will also offer the mechanical support, and it enhances the property of the polymer for the product, final product that we prepare. Blowing agents and surfactants are used mainly when we have to prepare polyurethane foams, cushions. Okay, so the polyurethane forms, to get that air has to be entrapped in between the polymer chains when solidification reaction takes place or solidification rate takes place. Air should be trapped there. Therefore, blowing agents are used. They can even control the formation of bubbles during the synthesis and to control the foam cell structure. A uniform cell structure should be created. A uniform bubbles should be created. Then only the polymer will be having, all the article or the product which is prepared will be having uniform strength. Fillers are used to minimize the cost and improve the material's properties. If it is used to just to reduce cost, we simply call it as fillers. If it is improving the properties, we call it as enhancement of property, or we call it as reinforcing. Reinforcing is a word which is mainly used in composites. Okay, therefore it increases the stiffness and the tensile strength of the article which is made up of polyurethane. Flame retardants are used because polyurethane as such, it is highly flammable. Therefore, we know that polyurethane forms mainly, it will catch fire immediately. To reduce its flammability property, okay, flame retardants are also added along with the polyurethanes. Smoke retardants, when it catches fire, too much smoke it will produce, so that will cause us pollution. To avoid that rate of the smoke generation, smoke retardants are also used. Applications, different types of polyurethanes and their application. Polyurethane can be in the form of thermoplastic polyurethane. The thermoplastic polyurethanes are mainly used as the keyboard protector, the thin layer or the transparent layer, or the semi-transparent layer which which we keep on the laptop keyboard, over the keyboard, that is made up of polyurethane. The outer cases of mobile electronic devices are also made up of polyurethane. Then the instrument panel in the vehicles, automotive, car, or any other vehicle, the instrument panel which is present near to that, in front of the vehicle, inside the interior, that is mainly made up of polyurethanes. Then caster wheels, different power tools are prepared, sporting goods are prepared using polyurethane, medical devices are prepared, drive belts, footwear, inflatable rafts, a variety of extruded films, sheets are also the applications of thermoplastic polyurethane. Second one, that is flexible polyurethanes. Flexible polyurethanes, that is the foam or the cushion materials. Even it is used as a carpet underlays, and then furnitures, bedding, automotive interior parts, then packaging, then biomedical applications, and even the preparation of composites, especially with the nano composites. Rigid polyurethanes are used as thermal and sound insulator. Polyurethane ionomers. Ionomers means in which the ions are added into the polyurethane. Different ions are attached to the polyurethane molecule. They are used for artificial hurt because it can conduct the electricity to some extent. Therefore, the expansion and contraction of polyurethane article can be controlled with that presence of ionomer. Therefore, it is used in artificial heart. So very interesting topic, artificial heart. It is used as a connector tubing for heart pacemakers. It is used in a hemodialysis tubes. Then waterborne polyurethanes. They waterborne means water soluble form. They are used in coating as adhesive, as a sealant, or as a binder. So these are the different applications of polyurethanes. The next topic, that is polymer composites. Composite, it is a multi-phase material in which reinforcing pillars are integrated with the polymer matrix, resulting in synergistic mechanical properties that cannot be achieved from either component alone. That means polymer composite is a mixture of many materials. Maybe two materials or more than two materials are mixed. They are only physically mixed. There is no chemical reaction as such, but they work in synergy. They work together to give better mechanical property or any other property than the individual component which is having. That type of material we call it as composites. It may be metal matrix composites. It may be ceramic matrix composite. It may be polymer matrix composite, or it may be nano composite. So here our topic is polymer composite. That means the matrix, the main component present in that is polymer. So advanced polymer composites are traditionally used in aerospace industries, but these materials have now found applications in commercial industry as well. Since earlier, these polymer composites were prepared or manufactured mainly for the aerospace applications, where high temperature application, high impact resistant applications when were required. For that, it was used, it was costlier, but continuous production and improved technology, the cost of manufacturing reduced, and almost all commercial industry we are using advanced polymer composites. Examples like graphite epoxy composites, in which epoxy is the polymer. The main component of the composite is epoxy. Graphite is the filler. Then boron epoxy composite, in which boron is the filler, epoxy is the polymer which is used. Kevlar epoxy composite. Kevlar is a filler. Again, it's another polymer itself, but epoxy is the main component. The Kevlar epoxy composite. These are highly engineered polymer composite, or the polymer composites having engineering application or structural application. They're having better strength. When even compared to that of metals, they have a better strength. The reinforcement in composite. The reinforcement itself, the word itself say that it gives support for the mechanical property, or it gives strength. Reinforcing, supporting strength. When we say about whenever there is a war is happening, we say that we have to send the reinforcement. Reinforcement means supply. We need to supply extra to the material to make it better strength. So the reinforcement, it can be a fiber. In case of polymer composite, it can be a fiber form of reinforcement. It can be fabric particles. Fabric particle means our cloth, or the textile pieces, cut pieces can be used as a reinforcement. Or it can be whiskers, the powders form also can be used, or the pieces can also be used. Okay, it will increases the mechanical property of the composite. It provides superior levels of strength and stiffness to the composite. The common fiber reinforcement used are carbon or graphite aramid fiber, which we call as Kevlar. Kevlar we'll study, I'll explain in detail, that's why I kept it highlighted. Then glass fibers are also used. The fibers which are made from the glass, the normal ordinary glass, in the form of fibers, they also be used as a reinforcement. Ultra high molecular weight polyethylene, that is UHMWPE fibers are also used. Then exotic fibers like boron, or natural fibers can also be used, like natural cotton or wool, etc. cannot be used. Many plant fibers are there. They also can be used as a reinforcement. In detail about Kevlar fiber. Kevlar, it is a type of aramid fiber. Aramid means aromatic amide. Okay, amides are having functional group NHCO. NHCO functional group we call it as a amide functional group, and aramids are the aromatic polyamides. They are amides which are having aromatic nature, means benzene or related aromatic compounds are there in the structure, and we call it as aromatic amide or aramid. They are class of highly heat resistant and strong synthetic fiber. Synthesis of Kevlar. Kevlar is prepared from one of the monomer 1,4-phenylene diamine or paraphenylene diamine. Paraphenylene diamine structure I am drawing. C6H4NH2 NH2, that is paraphenylene diamine, and terthalyl chloride. Terthalyl chloride structure I am drawing. C double bond O Cl, again benzene containing another C double bond O Cl. Both cases they are para position to each other, the opposite side of the benzene ring. Okay, now here a typical condensation reaction takes place. The HCl molecule will be condensed between that of diamine and the terthalyl chloride. If n number of paraphenylene diamine is used and n number of tertiary chloride is present, then more condensation takes place in this corner. As you can see, one more H will be combined with another Cl. Here Cl will be combined with another H. Okay, so we'll be getting 2 NHCl molecule will be condensed out, removed. Then remaining structure can draw. Remaining structure will be having only that much. This hydrogen present here, that is removed, therefore I am not including here. Then NH is there, then N single bond carbon, double bond O connected to benzene ring, C double bond O, then it is connected. So I'm extending that one to make it as a polymer structure. Okay, so it repeats n times. So here we can see NHCO, this is the amide functional group. Okay, so it also contains the aromatic benzene ring. Therefore, it is a aramid. It is a polyaramid. It's a polymer, so it repeats. This much structure repeats n times. Therefore, we call it as polyaramid. Therefore, this is the synthesis of Kevlar. Okay, so Kevlar it is synthesized using paraphenylene diamine or 1,4-phenylene diamine and tertiary chloride. It will give Kevlar, and hydrochloric acid as the byproduct. Now, structure and properties. The fiber has a high tensile strength and a relatively high density due to many interchain hydrogen bonds between the carbonyl groups and NHs and S. Okay, I'll explain in detail. Additional strength is derived from aromatic stacking interaction between adjacent strands. That also I can explain. So I'll take an example of one of the structure in the Kevlar. You can see it consists of NHCO, C6H4, NHCO, C6H4. That is the polymer chain. So I took only the C double bond of part of one polymer chain, and another polymer chain which contain the NH group. So you have seen in the previous slide that structure of Kevlar fiber. This polymer structure repeats here. It is the RMF where it is moving. That there a polymer is there, if just imagine, but only I represent the C double bond O part here. Here again another polymer chain is present at the bottom of this slide. You just imagine that it is there, but I took only the NH of that. So I just want to explain the hydrogen bonding. So here we can say a carbonyl functional group. This is a carbonyl functional group, C double bond O, in which oxygen will attract more electron density from this between that of carbon and oxygen. It become partially negatively charged, and carbon will be partially positively charged. That already you know, it is inductive effect or the corresponding mesomeric effect, that anything you can connect when benzene ring is there, therefore you can connect it to that. Here simply take the inductive effect, or somehow the charge separation is possible. Electron displacement effect is there, therefore the oxygen is more electronegative and it gets more electron density. In the same way, between NH, nitrogen will be having more electron density, hydrogen will having less electron density. Therefore, in actual practice, we can say that the oxygen having more electron density, the hydrogen having a less electron density. That means they can interact. Here more electrons are there, here less electron is there. Therefore, it can attract to each other, which we call as the hydrogen bonding. That is the bonding between hydrogen and electropositive hydrogen and more electronegative atom like oxygen, sulfur, nitrogen, that we call as the hydrogen bond. Now here it is between two chains or two molecules. So therefore, it is intermolecular and it is polymer chain. Therefore, you can call as interchain hydrogen bonding. Therefore, due to many such interchain hydrogen bonds between the carbonyl groups and NH centers, we have it gives a better strength. Therefore, they will come closer to each other. They will contribute towards its strength. Now, the second one, that is the aromatic stacking. I'm drawing the structure of that benzene which is present in that benzene molecule which is present in that. So one polymer chain, another polymer chain. These two benzene, because it has got the electron density at the center, which is aromatic nature. So continuously the electron density is moving towards between those carbon atoms. And when they come together, when two aromatic molecules come together, they also will share their electron density. That we call as the aromatic stacking interaction. It can be a displaced type of interaction. It can be edge to face interaction. It can be sandwich type interaction. But when two aromatic molecules come closer to each other, they have aromatic stacking interaction. Because of that stacking interaction, they are more attracted to each other. Therefore, again, it improves strength. Where if you want to break this molecule, we need not only breaking the other bonds, even we have to give extra energy, have to give to break the hydrogen bond as well as this aromatic stacking interaction. Therefore, that extra energy that we use, that indicates the strength of that polymer. So Kevlar fiber, it is having extremely high strength, tensile strength, and high density. High density means close packing. Density is nothing but mass per volume. Therefore, more number of mass will be present in a given volume because they are closely packed. That gives the additional, the extraordinary property of that Kevlar is due to the intermolecular hydrogen bonding as well as the aromatic stacking interactions. Okay, now that one only represented here between two polymer chains. Between oxygen and hydrogen, there is a hydrogen bonding, and between the benzene rings or aromatic molecules, there is aromatic stacking interactions. Now the grades and applications of fiber. Grades are not that much important for us now, but application, to represent the application, I'm given also the grades. When you do more research in Kevlar fiber, then you may have to have knowledge about the different grades are used, like K29, K49, K100, 190, 129, 149, and KM2. So generally, I can say Kevlar fibers are used as cables. They are used as asbestos replacement. They are used in tires, brake lining, cable and rope products. They mainly used in ballistic applications where high impact strength it can be draw. It can even block the bullets. Okay, so even armor, ballistic armor, and aerospace application, wherever we have to have a better impact resistance. Speed and any particle which is coming at maximum speed should be able to block it or withstand that impact. We call it as ballistic applications or aerospace application also. Even KM2, it has got enhanced ballistic resistance and it is used in armor applications. So very interesting applications for Kevlar fiber. So this many classes are available in my YouTube channel, My Intuition. Please don't forget to subscribe to my YouTube channel. Only your subscription is my strength. Thank you very much for watching my classes. Have a nice day. Thank you.